Thank you so much, JD, and the other organizers for the invitation. I'm going to try to give a talk about the geometric fixed points of real TC. In case my energy level goes down throughout the talk, I'm just sitting in my office. Please, feel free to just shake me up a little bit and let me know if I should pick up my voice or something. Right. So I'm going to start this talk by giving a brief crash course overview on usual TC, and then we're gonna talk about what this term real means. So let me start with the first section. It's called THH and TC, just classic. So what's this about? So we start with a ring spectrum. Let's call it A, and you want to define some other spectrum out of it. Let's call it THH. And as a spectrum, this is, well, you can take A and look at it as an AA bimodule, and then you can tensor it with itself over A of tensor A. And now here, you get a spectrum. And here, I'm going to try to do during the talk, tensor means tensor over the sphere, or also known as this mesh product. I hope I'm not going to get in trouble later on with the usual tensor product of abelian groups, but let's see. Okay, so this is a spectrum you can get out. But if you are a bit more clever, you can actually see that this has more structure. So another way of writing this, and if you think in terms of maybe the bar resolution for setting up the usual derived tensor product, another way of writing it is as some big bar construction. So you can write it as the realization of some simplicial object that takes, whose n simplices are n+1 copies of A, tensor with themselves, with itself. And so this is n+1 factors. And I write them in a circle so that you can see what the structural maps are. At least the face maps just multiply adjacent copies of A. And if you set it up like this, maybe you notice that in degree n, you have an action of the group, the secret group of order n+1. And if you write down what the compatibility condition with the face structure is, you get a cyclic object in the sense of con, and therefore this defines a spectrum with S1 action. Spectrum with S1 action. Okay, so at the very least we get that. But now we need to be careful what you mean by that. And I guess so far I just meant literally a spectrum with an action of the circle. And if you are careful, you can actually promote this to what's called a genuine S1 spectrum. And there are basically two ways of doing this. Let me tell you how to do that just very briefly. So this can be promoted to a genuine S1 spectrum. In basically two ways. So either classically via setting up, let me just say, setting up carefully this bar construction. In point set models. And this was the classical approach of Buxet, Shang, and Madsen. More recently, by defining a certain map, which is called the Frobenius, or via the Frobenius, which is a certain map from this THH of A to its state construction for the group CP. Okay, but either ways, no matter what approach you use, you get a genuine S1 spectrum, or to be really careful, you get a spectrum with the action of the finite subgroups of the circle. And the spectrum has a property that the geometric fixed points are equivalent to the underlying spectrum. So we get something like that, such that the geometric fixed points by all of the finite subgroups of the circle are actually equivalent to the origin. And something either with this property or with this property is called a cyclotomic spectrum. Once you set this up, you can define TC, so topological cyclic homology at a given prime P can be defined as a limit of a big diagram that you can set up using the fixed points of A, of this THH. So these are another type of fixed points called the genuine fixed points, maybe that are part of the structure of this genuineness one spectrum. And these maps are called, one is called R, the other is called F. F simply comes from the fact that a small cyclic group sits inside a bigger cyclic group, and this R is a bit more complicated and is defined from this Frobenius. And right, so this was the classical definition of Böxel, Chang, and Madsen, and then Nikolaus and Scholze came up and realized that there is a way of describing this without talking about these genuine fixed points. So Nikolaus and Scholze prove that if A is bounded below, then this TC of AP, at least after AP complete, is equivalent to an equalizer of two maps on two constructions that do not use this genuine equivalent structure, but only this Frobenius map here. So let's see. We take the homotopy fixed points by the infinite cyclic group over the P inside of the circle, and on the right, let's see, more space. On the right, you can take first a Tate construction, and then homotopy fixed points. And there are two maps here. One is given by this Frobenius, and then there is another canonical map that basically isolates a first copy of CP, maps it to its state canonically, and then take. And then, yeah, so let me not say too much about that. It's a canonical map. Okay, so the point is that they find out a nice, neat formula of this TC as a certain equalizer, and then you can use this equalizer to do computations fairly, well, maybe not easily, but more easily than you would before. Right, so this is, by this formula, this is a computable object. Now, why would you care about this object? Well, I think Andrew has talked about it already earlier, but let me say something. That there is a trace map from algebraic K theory of A, at least if A is connective, into TC, that has nice properties after T completion. Oops. And there are lots of calculations about K theory that leverage the fact that you can compute TC and the fact that this map is nice. Nice means, for example, the fiber is nil invariant, and yeah, and you can do lots of calculations. Okay, so this was my 10 minutes crash course on TC. But the important thing is it tells about K theory, and there is a nice equalizer that you can use for computing. Now, let me tell you what happens for what is real version of this story is about. So, real THJ and real TC. the idea is to lift this construction. So if we look at our bar construction at the beginning, let's see, this one, what did we use? We used this S1 action, which is given by rotating this tensor product. Now there is an extra structure that you can try to exploit on the circle, which is the reflection along some axis. So we'd like to basically endow this object with a Z-mod2 action, or maybe even better, the structure of a genuine Z-mod2 spectrum, by exploiting this reflection along the horizontal axis. And that's the idea of real THH and real TC. So idea is, let's say, refine THH and TC to genuine Z-mod2 spectrum by exploiting the reflection of S1. And if you just try to naively just do that on this bar construction, you get in trouble because this is not compatible with the simplicial structure. And so what you need is some extra structure on your ring to make this work. So we need some extra structure on it. And okay, let me tell you a little bit about this extra structure. What is it? There are different ways of setting it up, and I'm going to try to do it in the most, I don't know, model independent. Maybe that's not really the right, well, the least pointed way I know how to do it. So let me recall you that the Hill-Hopkins-Ravalan norm is a construction of a ring spectrum A, and I'm only interested in the group Z-mod2, so I'm gonna, this is something you can do for every group, find a group at least, and I'm gonna take the group to be Z-mod2. Is the ring spectrum, well, oops, the C2 equivalent ring spectrum. And so it's called N of A, and I call it just N without, I should put a C2 and an E maybe there, but I'm only interested in this one, so I'm just going to call it N. And well, one way of setting it up in Poinsett-Land is to say, well, take A, smash it with itself, and then you act via the flip action of Z-mod2. And at very least, if A is flat, then this Poinsett model in orthogonal spectra, say, actually gives you the right equivalent homotopy type. But regardless how you want to set it up, its fixed points fit in the following square. So its fixed points fit into a pullback. So you take this norm. So what are the Z-mod2 fixed points of this? This is the isotropy separation square, and well, the underlying spectrum, we said it's A tensor A with the flip. So we take homotopy fixed points of that. You map here the homotopy orbits of the same spectrum map in, and you take the co-fiber, which is by definition Tate. Oops, I'm mixing up my C2s and my Z-mod2s. I'm going to get even more in trouble later, but I'm going to try to be consistent. I'll call it Z-mod2 for now. And then here, you need to put something. You can put anything you want. And this is going to be the geometric fixed point spectrum of this norm. And the geometric fixed points are the spectrum itself. And this map down here is what's called a Tate diagonal. And then it turns out that squares like this are actually determined as a Z-mod2 spectrum, and that's the one I want to look at. And in fact, all of these maps are multiplicative. And so this is, in fact, determines this as a ring spectrum. Okay, and why am I talking about the norm is that using this norm of A, we can formulate the extra structure we want on A itself to be able to take real THH. So here is what structure we need. So suppose that A, which is a ring spectrum, actually, maybe let me remind it, so that the ring spectrum A is moreover a ZMO2 spectrum. So it has a ZMO2 action and some notion of genuine fixed points attached to it. And then we need to say how the multiplication, so this has nothing to do, being a ZMO2 spectrum has nothing to do with the multiplication. Now we need to somehow give some compatibility or some extra structure that links together the ZMO2 structure of this ZMO2 spectrum and the multiplication of A. And this is done via the norm. So together with a left module structure, which is, so we asked that the norm, which is a ZMO2 ring spectrum, acts on this spectrum A. Okay. And then there are conditions. You want basically the involution of this equivalent spectrum to be a map from A up to A. So this is the involution that comes with the fact that A is a ZMO2 spectrum. And now, but you need to be a bit careful. You need to say this coherently. But if you model this with, say, orthogonal spectra with involutions, then there's no extra coherence, everything is strict. And then second, you want to link this module structure with the multiplication of A. And then you can just say that the underlying map of this thing is basically the triple multiplication. So the underlying map of the module structure is, well, so it's some map like that. Remember, the norm, the underlying spectrum is just A tensor A. So it's some map like that. And it's this triple multiplication, but just with some permutation in to make things work. And I apologize, I'm going to write down elements for describing this map instead of diagrams. And then what do is basically you act by A on the left and by B bar on the right. That's the underlying map. Okay, so let me recap. We have a ring spectrum, which is moreover a ZMO2 spectrum and has an action of the norm. And it satisfies these conditions. So once you're here, you can then define, there's a sort of definition of real THH, which is quite straightforward, is, well, let's take A, just told you it's a module over the norm. And because of this op, you can turn a left module into a right module. So it's also a right module over the norm, and you can just tensor them together. And I think this is a definition of real THH, which is quite convenient. And if you do this, well, this is in the land of C2 spectrum. So you get a C2 spectrum automatically. Let me call it ZMO2. And again, if you set this up more carefully, you can actually incorporate the S1 action as well. So you can write this down as some, I think I'm just gonna draw the same picture I did before. Just tensor them in a circle, and then you have an extra involution that comes from this reflection here. And if you set it up carefully, you get out an O2 spectrum. Which is the usual S1 action as we said before, and then plus these reflections act by reflecting these. right? And then once you do that, you define TC the same way. So you define TC, real TC at a prime, basically as the same limit, just now everything happens in the category. So, oops, in the category of Z2 spectra. So you can take THR. So this is an action of O2, and you take the fixed points by some cyclic group. And this is an action of the Y group. And so you see this reflection still acting on these fixed points. So this is now a diagram of Z2 spectrum. That's how you get this extra involution TC. But it's crucial that you need to use this extra structure on the of this module over the norm and start with something that has itself a Z2 action. Otherwise, you're not going to be able to lift this whole construction. And then there is a theorem that tells you that in fact you can write this down much more easily as an equalizer. So this is the theorem of Quigley and Shah, and tells you that if A is bounded below, then I'm basically going to write the same thing. So I'm going to write that this real TC at P, this P completed, is the same as an equalizer of, again, two maps. Frobenius and canonical. And then you need to be super careful how you set this up, but I'm going to just write the same thing. And let me just say, for this construction need to be carried out relative to this residuals and not to action. So let's say carefully carried out in Z2 spectra again. Okay, so far we have constructed an object which lifts the usual topological cyclic homology. And well, now where is the K theory? I mean, what can one use this for? And let's see. And there is a theorem that tells us that this is useful for studying something. And this is a theorem of Harpaz, Nikolaus, Shah. And it says the following: there's no more K theory, but there is L theory instead. I'm not going to talk about L theory much. It's just some groups that you can build out of forms over your ring. So let me just say that, and so their theorem, and this is inspired by, it's a slight tweak of a conjecture of Weiss and Rogness. So after a conjecture. Weiss, Rogness. And they show that you can take TCR and we take it at the prime 2. And this is it's on Z2 spectrum. And so you can apply the geometric fixed points by Z2. And this is the cofiber of a certain map in L theory. And this is quadratic L theory. As defined, well, if A is discrete, or if A is discrete, then this was defined by Ranitsky, and then Lurie has extended this whole theory to ring spectra, and in fact, much more generally to what's called Poincaré infinity categories. And this one is the L theory of a different Poincaré category. So this is another flavor of L theory. You can just give it a name. It's called genuine L theory. And again, after Lurie, but I guess the point is that L is an object defined from forms. On A. And this one from quadratic form, and this one from another kind of forms. So you can still use this to compute something of a k-theoretic flavor, maybe that here. Okay, so this is just motivation. And now, because this is a computational seminar, I'm going to tell you how you can try to compute this thing. And so from now on, I'm only going to be concerned basically with the geometric fixed points of this spectrum. So here's the theorem I want to talk about, which is in joint work with Moy and Bashkorian. And is the following. So suppose A bounded below. Then two things happen. First, for P odd, nothing happens, nothing interesting. And this is why we use only the prime 2 up here. So for P odd, if you take this TC at the prime P, then you only get THH back. Basically, this whole limit doesn't really do anything. And moreover, this is equivalent. I mean, this is actually quite straightforward from the definition I gave. What happens if you take geometric fixed points? Everything is monoidal. So you get the geometric fixed points of this times of the geometric fixed points of the same thing over the geometric fixed points of the norm, which is A. So I should have probably said this formula before, but let me put it now. So this you get the geometric fixed points of A tensor geometric fixed points of A over A. And maybe because this, so for some module structure you get the geometric fixed points, and because this is gonna pop up so prominently in the calculation, let me tell you what it is. So let me spell it out. So where A, the geometric fixed points, is an A module via, and we call this the Frobenius module structure. There's a lot of Frobeniuses in the story, but I think it does kind of deserve the name. So what is it? Is you have this action of the norm on A, and you just apply geometric fixed points to it. So and what do you get? Well, because the geometric fixed points functor is monoidal, you get that this is equivalent to the geometric fixed point of the norm, which is A, tensor the geometric fixed points. So this computes real TC at an odd prime in terms of the geometric fixed points of the ring. So that leaves us with the prime 2, and that's the interesting prime. So for P equal 2, which is the one that by the theorem above relates to L theory, for the prime 2, we find that TCR of A at the prime 2, if you take the geometric fixed points, and you get an equalizer again. So this is very much in the spirit of Nikolaus and Scholze and Grisha try to write down this TC as an equalizer. And this equalizer is fairly computable. We're going to see in a second. Well, at least some examples. So you take A, we just saw that by default, A is a module over the norm. So you get tensor it over the norm of A with some other module over the norm. But we saw that A is the geometric fixed points of A is a module over A. And so if you norm it, you get the module over the norm. Parenthesize like that. It's something you can do. And this is some Z12 spectrum. And so we take fixed points. Oops, I'm trying to keep it as Z12. Okay, and then this is the source of our equalizer. And then there are two maps, two basically the same thing without the fixed points, one of which is just a map that forgets the fixed points. But what is the underlying spectrum of this? Because the underlying spectrum of the norm is A tensor A, the underlying thing is just the geometric fixed points. Tensor of A, the geometric. So basically, this thing is the geometric fixed points of real THH. Okay. And these maps are, there's something that looks like a Frobenius and something that is going to look like some restriction. Yeah, and I'm not going to insist on what these maps are, but there is an equalizer like that. And maybe let me say something. This is related. So this formula is related to an equalizer. To an equalizer that shows up in the proof of this L theory statement that I gave above. So the way to they compare TC to this L theory thing is also via some sort of equalizer formula. So these two are related. In the proof of the theorem of Harbatz, Nikolaus, and Shah. Okay, so what have we got? We have cooked up some spectrum that relates to L theory and then that has a nice equalizer description. And in the last 15-ish minutes, I'm going to try to give you an example of how you can compute this equalizer. And so section 3 is calculations. Okay, so here is something we've been, actually, let me give you a theorem where I give you a few calculations in one, and then we're going to see, maybe try to sketch the proof of one of them. So here's a theorem. Again, I'm trying to work with more input volume. So the first is, if you take a field of characteristic 2, perfect. So perfect means that the Frobenius, if you square, the square map from K to itself is an isomorphism. And then TCR K at the prime 2 is, if you take the geometric fixed points, is a wedge of, so it starts in degree -1, and it has the co-kernel of the Frobenius and the identity, plus the identity. As maps on, okay. And then in even degrees, it has a copy of F2. And we have been after this thing for a long time and we couldn't figure it out. So if Y characteristic 2, if the characteristic is odd, then these geometric fixed points vanish and this is 0. There's nothing interesting. So really characteristic 2 is the interesting case. And then we get this. And this is also, so this is also proved by Quigley and Shah. Straight from the other equalizer I was talking about before. And in fact, from here we are able to deduce the full equivariant homotopy type of this. Maybe let me not insist on that. So this one you can calculate, and then another thing you can do that is actually, I think, maybe even nicer, is we can do Z. And why is it nicer? Because the L theory of Z has a Z modulating degree 0, this normal, this cofiber I was talking about before. And that 8 picks up the fact that the symmetrization map from quadratic to symmetric L theory is multiplication by 8. This has to do with the signature mod 8. And we can see this in this calculation. So again, this starts in degree -1. This one is 4 periodic. Whenever it's not 0. It starts in degree -1 with an F2. And then in degree 0, mod 4, it has the Z mod 8s. And then in degree 1, it has F2s again, and then in degree 2, there's nothing. And so maybe let me point out that in view of the theorem about L theory before, you could actually compute the L theory of perfect fields and the L theory of Z. And so you can, you don't get anything new out. But maybe one thing new that you can get from our theorem is that there is a base change formula you can use to extend these calculations to perfect FP algebras, perfect F2 algebras, and here to certain torsion-free rings. So maybe let me say that too. So these calculations can be extended. Via base change. Well, the first one to perfect FP algebras by base changing from F2. And the second to two torsion-free rings with perfect modulo 2 reduction. And
sorry to interrupt.
Yeah.
There's a question in the chat. Are the geometric fixed points of TCR always generalized to Eilenberg-MacLane?
Yes, but it's not obvious at all. So it's not obvious a priori that it is. So they're all, so all of these things are multiplicative, and they're all modules of TCR of Z. And so yes, but it's not clear a priori that they are, especially this equalizer. This equalizer here, even if you can show that the terms are Eilenberg-MacLane, which they are if you input discrete rings, for example, but then these maps are not linear. So it's not clear that they are. So it's a kind of a consequence a posteriori. Yeah. Right, so for perfect S2 algebras and for perfect rings, which are two torsion free, for example, the two adix. So. And this, I'm not sure if you can compute groups of perfect S2 algebras that well, possibly, but I think D is not so much. I mean, the two adix, yes, but in general, these two torsion free things with perfect modulo 2 reduction, I don't think so. And this is really, the computation really comes out of this equalizer that is just not available for theory directly. And let's see, I got 5 minutes. Maybe I'm going to say just something for F2. So how do you get started? So proof, sketch for F2. Go for, let's see. Actually, F2 doesn't matter. Let's do it for F2. So the same strategy works for perfect fields. So what is the key? The key is that gets you even started is that, well, of course, if you take the geometric fixed points of F2, this split like that. So it's a copy of F2 in each degree. And here you need to be super careful how you split this. So this thing is a module over F2 in two ways, via the Frobenius and via the map from the genuine fixed points, which is also F2. And you need to choose one of those two things. And unchoice is going to give you a splitting, and this is going to have repercussions later. But let's say we split with Frobenius. Then what we need to compute in our equalizer, the term that appears in the equalizer is this one, is the tensor product of K over the norm with its geometric fixed points. But because this splits, you just plug it in and then be careful a bit what the norm does on these wedges. You find that this is equal to a big wedge of things. You've got some suspensions by the regular representation, and then some induced terms. It's going to look like that. Oops, and now I'm writing K. I meant F2. Right, and so now you can compute the fixed points of this by, well, here is no problem, these are induced, so the fixed points, you just kill off this C2 basically. And now here you need to compute fixed points of some suspensions by the regular representation, and this boils down to some calculation in Verdon homology, but you can compute what it is, and it's not so bad. So let me do like this. So these contribute, let's see. And so these terms, this goes away. And here you get, see, so you get some more copies of your F2s. It's going to look like that. And then you need to compute the maps. So and here is where I want to make a point, whatever the computation is. Here is where it gets tricky, because we have chosen to split this with Frobenius. And this has the effect that only one of these maps is linear and not the other. And if you chose to split with the other module structure, then the other map is going to be linear out of the first. So no matter what you do, you are a bit in trouble. You cannot just describe this map as on the wedge summons directly. There are some higher cohomological operations that show up. But it turns out that you can just compute them on homotopy groups, and that's going to be sufficient. So let me say only one of R and F is linear over XZ. But you can still show that, that R minus F, so we want the equalizer of R and F, so we're equivalent to the fiber of R minus F, and this map R minus F is an equivalence on odd degrees. Because that you can get to only test in homotopy groups, and then this gives you some. So the long exact sequence defined by this equalizer or by R minus F split, and you get pi to L of what you wanted maps into some big sum of F2s. Then you've got your map R minus F, some other big sum of F2s, and then the lower homotopy group that you want to compute. And I'm out of time. So if you do some yoga with R minus F, you're gonna see that basically this is an isomorphism on, let me see. So these sums are all indexed on the same thing. And this R minus F is an isomorphism if you restrict it to the non-diagonal terms. And then you can compute what it does on this n plus m is equal to L term. And then you get that pi to L is equal to pi to L minus 1. They're both of those. So what I want. And for Z, it's a similar strategy. It just becomes much more complicated because these terms don't look that nice. And you always need to fight your way through, but somehow computations are more or less in reach. All right, I'm gonna stop now. Sorry for going over time.